I'm going to share my screen. I hope it is visible, right? Okay, so let's start today's session. So the course name is User Neutral Particle Physics, and this is for the week 4 assignment for previous year question papers solution. And let's start. Okay, so this is the question number 1. Kinetic energy of alpha particle in an alpha decay is 7.68 megaelectron-volt. If Q of the kinetic energy, we are discussing the first question. The first question is kinetic energy of alpha particle in an alpha decay is 7.68 MeV. If Q value of the decay is 7.82 MeV, the mass number of the parent nucleus is how much? Okay, so this is the question, and we need to answer the question. So here, as we have already discussed the expression for this question in the class, so I am just going to use that one. So let's say this is, okay, what are the given values here? The given is like the kinetic energy of alpha particle, so alpha k, let's say, so it is like 7.68 MeV. Now what else it is given? The Q value is given as 7.82 MeV, right? So these two has already given. So what will be the expression? Expression is like Q, that means the Q value of this system of the decay, that is equals to alpha k into 1 plus m of alpha divided by m of d, right? So what is m of alpha and m of d? M of alpha is nothing but m of alpha is mass of alpha particle, right? And m of d, what is m of d? M of d means like mass of daughter particle. So this is the thing, and this is the expression for calculating the Q value. So here they are asking that what will be the mass number of the parent nucleus. So this is the expression, and they are asking that what will be the mass number of parent nucleus. That means they are asking that what will be m of p, right? So what does this mean? So m of p, m of p means like so this is, let's say, x, and this is y, so it is z and a. So for alpha decay, so what will happen? Z minus 2 and then a minus 4. So like that. So like this is the parent particle, and this is the daughter particle, and this is the alpha particle. So here, as I told you, Q equals to the alpha t into 1 plus m alpha by md. So as we have this one, we have this one, we have also this one. This one is like very near to 4. So that's why we will write it as 4, and we will just calculate the value of md. And from md, mp will be nothing but md plus m alpha, right? So I have already calculated it here. It is like Q equals to T into, okay, here I just mentioned T as a kinetic energy of a particle, then 1 plus md by m alpha by md. So now you can see, so if I just simplify that one, that will be like md plus m alpha, okay? So this md plus m alpha is nothing but mp divided by md. In terms of mp, how it will be? It will be mp minus 4, because mp is equals to md plus m alpha. So that's why I have written here mp divided by mp minus 4. 4 is m alpha, okay? So as Q equals to 7.82, 7.68. so the value of MD will be like that. So it is like 223. So in terms of MD also I can calculate. So at that time it will be like 219. Then it will come as 223 as MP. So as obviously the mass of the daughter particle they have written as it should be in right integer value. So that's why I have just written here as a 223. So maybe I have calculated that one correctly, or maybe I can check once again also. So MP, okay. So yeah, fine. So it is like 1 plus 4 divided by MD equals to Q divided by, that means 8 divided by 6.8, right? So 7.82 minus 7.68 divided by 7.68. So 4 by MD, that is equals to 0.0182. So MD will be 4 divided by answer, so which is 219, right? MD is 219. So if MD is 219, that means MD will be 223. MD will be 219 plus 4, that is 223. And it's very simple because previously also we did that one. Am I audible by the way? I think I am audible. Yes. Okay, so coming to the next question. The next question is kinetic energy of alpha particle in an alpha decay is this one. If the Q value of the decay is alpha, the mass number of the parent nucleus is how much? So it's exactly very similar to the first one. So if you people want to calculate that one, then you can calculate, or otherwise I will do it a very simple, very quick thing. I mean there is no new thing, right? Because Q is like T into 1 plus M alpha divided by MD. And they are asking that mass number of the parent nucleus, exactly similar to the previous one. So it will be like here MP minus 4 and here MP. So and Q is given as T as given, M alpha is given as 4. So Q is 8.38, 8.23, 8.38, 8.23, right? So Q equals to T into 1 plus 4 by MD. Which one you prefer, you can just use that expression, no problem. So 1 plus 4 by MD is equals to 8.38 divided by 8.23. So it will be 4 by MD equals to 8.38 minus 8.23 divided by 8.23. Okay. So the value will be like 8.38 minus 8.23 divided by 8. Divided by 8.23. Yes. So it is 0.01822. So MD will be 4 divided by answer. This one. So what will be MP? MP will be like 219.466 plus 4, which will be like 223.46. It can be approximately write it as 2, 2, 4, because it is 5 and 5 or more than 5, it will come as 2 to 4. Or it can be written as 2 to 3 also, like it's not that much problematic because there will be a range of, it's this 0.46 difference, so it can be fine. So we have already explained the first two questions. If you have any doubt on these first two questions, you can ask me. I think it's very simple, so that's why you people maybe don't have any question on that. Can you hear my voice? Yes?
Yes, ma'am, you're audible.
Okay, fine. Now question number 3. So question number 3 is kinetic energy of alpha particle in an alpha decay is 8.30 MeV. Then the mass number of daughter particle is 201. What is the Q value of the decay? So it's exactly the similar one whatever the previous expression was there, but the given parameter is a little bit different. So that's it. So again I'm just going to do that one quickly. So here what is the given values? Given parameter is like kinetic energy, that means T is 8.3 MeV. Now the mass number of the daughter particle, that means MD is given as 0201. They are asking that what will be the value of Q. Okay, so the Q is obviously T into 1 plus M alpha divided by MD, and M alpha is given as 4. So they are asking about T value, so T is 8.3. 8.3 was there? 201. Okay, so 1 plus 4 divided by 201. Okay, so if I just calculate that one, 4 divided by 201 plus 1 into 8.3, it is 8.465 MeV. So what is the value, Q value of the decay? The Q value of the decay will be 8.465 MeV, right? Because it's already given the MD and M alpha and T given. So from that equation we can have the value of Q. What is the Q value? They are asking that Q value. This is 8.465 MeV. Okay, so maybe we will go to the next question again. See, whenever it will be a little bit tricky question, I will take some more time on that. But if it is a very simple question, then we can go directly to the next question. Obviously, if there is some doubt, obviously you will ask me. But otherwise, we can go to the next question. Right? So the kinetic energy of the alpha particle in an alpha decay is 5 MeV. Mass of the daughter particle is 98. What is the value of Q decay? Exactly similar to the previous one. So just do that one quickly. So it is T is like MeV, 5 MeV. MD is given as 98. What will be the value of Q value, right? So Q will be T 1 plus M alpha MD. I mean, so many times I have written that one, so I just remember that one. 1 plus 4 divided by MD is how much? MD is 98. Daughter particle is given as yes, daughter particle is given as 98. Okay, so the value will be 4 divided by 98 plus 1 into 5. So it will be 5.204 MeV. So the Q value will be 5.204 MeV. So we have done that one. So now, yes, this one will take a little bit more time. So we will focus on this question a little bit more. Okay, by the way, the first 4 questions, I think it's very simple. Like the same expression is there. The expression was similar exactly. Q equals to K alpha 1 plus M alpha divided by MD. By the way, like I'm just using these notations different in different terms, so it's not that much problematic. Whatever you want, like that, in your convenience, you can just use the notation, but the meaning should be same. Okay. Okay, so now coming to the next question. So next question, maybe it will take some time to understand, so that's why we will just see a little bit with clearly. In the beta decay of Sn to Sb, the maximum kinetic energy of the electrons emitted is found to be 3.2 MeV. If the atomic mass of Sn is 126.910360 U, the atomic mass of Sb 127 is how much? Take 1 U equals to 931.5 MeV. Okay. So first of all, I just want to remember one thing. Before some week, maybe in the 3rd week or maybe in the 2nd week, I was talking about the Q expression. Like the Q expression means Q value of a decay will be like the nuclear mass of a parent nucleus minus the nuclear mass of the daughter nucleuses. I mean, whatever, how many daughter nucleus will be there. So the mass difference between the parent nucleus and the daughter nucleus will give the Q value. But the mass difference means the mass of the nuclear mass. Okay. So here you have to think about little bit what is the what is given here and what they are asking for. They are asking for the atomic mass, and they are also giving the value of the atomic mass of the parent nucleus, right? So I have already told you what will be the difference between atomic mass and nuclear mass, but still as this is the first time in this question we are applying the expression, the difference between atomic and nuclear mass. So I'll little bit more talk about nuclear and atomic mass difference, so that it will be clear for all of you. So yeah, basically like Q value, Q can be written as nuclear mass of parent particle minus nuclear mass of daughter particles. So why I am writing here particles? Because they may, if let's say the daughter, after the decay there is more than one particles are present. So that means whatever the masses, whatever the particles are there as a decay one with the final state, that all the nuclear masses of these daughter particles will be added, and after that will be subtracted from the nuclear mass of parent particle. That will give the value of the Q value. Okay. So this is the nuclear mass term in terms of nuclear mass. Now what will be in terms of atomic mass? So let's say I have one particle which is XZA. Okay. So what does this mean? This means that the proton number for X is Z, proton equals to Z, neutron equals to A minus Z, right? So these two are there, and electron. How many electrons are there? Electrons is Z, because the atom is neutron, so obviously the number of electron and number of proton will be same. So the Pu is Z, so E should be Z, and the number of neutron will be A minus Z. Okay. So now nuclear mass of X. What does this mean? This means that M of P. M of P into Z. That means, let's say I have Z number of protons, and each and every proton has the mass as MP. Okay, so that means each proton has mass MP, and I have Z number of protons. So the total number of total mass of the protons is Z into MP. Is it fine? Okay. Plus A minus Z into Mn. Why? Because Mn is, the number of neutron is A minus Z. So, and each and every neutron has the mass as Mn. So A minus Z into Mn. So these will be the nuclear mass of X. Now coming to the atomic mass. What will be the atomic mass? If I will talk about atomic mass, so atomic mass of X will be, whatever these things are there, that will be obviously same, like MP into Z plus A minus Z into Mn. Then with that there will be one term which will be added, which is Z into Me. Why? Because atom means what? Atom means it will consist of nucleus as well as electron. So if we will talk about atomic mass, that means the nuclear mass plus the mass of the electron, whatever it is present in that atom. Okay, so atomic mass of X is nothing but nuclear mass plus the mass of the electron in that system. So I hope it is clear. So now in that case they are telling that in the beta decay of Sn to Sb, the maximum kinetic energy of the electrons. Okay, the maximum kinetic energy of the electrons emitted. This phrase is nothing but the Q value. This is telling us a Q value. So the Q value will be the 3.2 for this question, and if the atomic mass of Sn is given as this one, atomic mass of Sb will be how much they are asking. So I have already told you what will be the Q value. Q value will be, let's say if Sn goes to Sb, okay, then Q value will be, okay, it is plus something electron, right? Electron, E minus. So the Q value will be the nuclear mass I am writing here n means nuclear mass, okay, nuclear, Nu, minus Sb of nuclear minus, okay, now E minus is not a nuclear, so obviously the mass of electron will be simply like that. So this is the case. This will be the exact formula for the Q value. Now they are giving us the value in terms of atomic mass. So we have to convert the atomic mass to the nuclear mass, and after that we will get the answer. Okay, fine. So now let's say atomic, I am just writing here atomic mass as like Sn A, AT, atomic mass. Okay. So this AT means I am just denoting as atomic mass, and Nu means the nuclear mass. Is it fine? Okay. So I need to do a relation between atomic mass and nuclear mass, so that I can just replace that Sn nuclear mass with the Sn atomic mass, which is given in that question. So how do I do that? So Sn atomic equals to Sn nuclear plus Me into something. What is something? The something means the number of proton and number of electron what is present in the Sn. So obviously it may, I mean, in most of the cases you might not to be remember that what will be the Z value of Sn, because in periodic table there will be so many particles and you don't need to remember all the particles Z and A value. So what we will do, let's say I am writing here as X. I don't know the value of X here, but I am writing here as X. So X into Me, that will be the atomic mass, is it? So Sn X nucleus, that will be Sn X atomic minus X Me. If you have any question, any doubt, you can just stop me and you can ask me, no problem on that. Up to this, is there any problem? Because this is nothing but a relation between atomic mass and the nuclear mass. And I don't know the exact value of the proton, so that's why I have just written here as X. So I just written here Sn X nuclear equals to Sn X atomic minus X Me. Does it make any sense?
Yes, ma'am. Understood.
Fine. Okay, so now what we will do? We will replace this expression here. So now you can see that, okay, here also they are asking in that question that what will be the atomic mass of Sb. So there obviously whatever we will get, that will be the atomic nuclear mass of Sb, but we need to know the atomic mass of Sb. So for that case, similarly whatever we have done to Sn, we will do with the Sb also. So now if I just write these things, then Q can be written as Sn X atomic minus X Me, X into Me, right? Now there will be something minus Me. Now in something what will be there? Okay, so maybe I don't have, I have space, okay, sorry. So now Sb nuclear, that should be something as a function of Sb atomic. We need to check that. So just remember these things. Sn was there, then Sb plus electron. It was the previous expression, it was the decay expression. So I don't know the value of this. So what will be this value? If I write here E minus is nothing but minus 1, 0. Okay. So if it is minus 1, 0, if it is X, then what will be the value of this one? Can anyone tell me? I mean the Z value of Sb. If a Z value of Sn is X and the daughter particle as electron minus 1, 0, to conserve the Z value, what will be the value of Sb here? I mean, what will be the Z value for Sb?
Ma'am, x plus 1.
X plus 1, because x plus 1 minus 1 will give us x. So that means if I am taking z value of Sn as Ax, I don't know the value, and in that question also it is not given. So that is the main problem, no? Because I don't know the value of x and it is also not given here. So I will put it as x, and for Sb obviously it should be x plus 1. Otherwise the z conjugation will not be valid. So now it is like Sb atomic minus x plus 1 into Me. Okay, so Sb nucleus equals to Sb atomic plus minus x plus 1 into Me. Now coming to the Q value again. So Q value was Sn nuclei minus Sb nuclei minus Me. It was the Q value. So if I just put these values, so it will be like Sn At minus x into Me, right? So this one was there, minus Sb. Sb is Sb At minus x plus 1 into Me minus Me. I'm just writing each and every step so that you can understand. So Sn At minus Sb At. Okay. Now you see that minus x Me minus minus plus x plus 1 Me minus Me. Okay, let me write this Me here, not here, but here somewhere. So this is simply a mathematics. So Sn At minus Sb At minus x Me plus x plus 1 Me minus Me. So the answer will be like Sn At minus Sb At. Now see, minus xme plus xme, xme will cancel out, plus me minus me, so that will also be cancelled out. So this will be nothing but Q value. So Q value will be Sn At minus Sb At. Now for the beta minus case, just remember that one. For beta plus case it will be little bit different, and I will come for the beta plus also, but little bit later. But for now, just see the expression. Q value for beta minus is nothing but atomic mass of the daughter parent nucleus and parent particle minus atomic mass of daughter particle. Now in that question it was written that 3.2 is equals to atomic mass of Sn is given like 126.910360 minus Sb of atomic, and they are asking that what will be the atomic mass of Sb. So simply we will write Sb of atomic is 126.91036 minus 3.2. Oh, so sorry. This should be transferred to MEV, and after that will be subtracted from, that 3.2 will be subtracted from this one, and after that we will put it in U value, like unit. This is simply a unit conversion calculation, because you understand that this is the MEV unit and this is the AU unit, AMU unit. So we have to convert that one, and after that we can get the answer. So let's do that one quickly. Maybe I don't have any space right now. Okay, I can do here also. So what we will do like, maybe if it is already given in EU unit in the answer also, so maybe we will convert all these things in EU unit. Okay, then it will be simply. So 1 U equals to 931.5 MeV. So 1 MeV will be how much? 1 MeV will be 1 by 931.5 U. Okay, so now there is 3.2 MeV. So not Q, Sb atomic will be 126 point, it's already written, I have written here, 126 0.91036 minus 91 how much 9103036 minus 3.2 divided by 931.5, and that will be whole in U unit. Why I have written here this term? Because 3.2 was in MeV unit and 1 MeV is equals to 1 by 931.5 U. So to convert MeV into U, I have just written here and then multiplied with 3.2. So just now calculate this one. This one is 126.91036 minus 3.2 divided by 931.5. Okay, so this is 126.906947 U. Now coming to the options here, 90692. Okay, see here 247 was there, so it can be written as 126.9069250. So this is nothing but option number A. So maybe it will be a little bit tricky for you people, because we have to convert the atomic mass into the in terms of nuclear mass, or vice versa, to calculate the exact number whatever they are asking in that question. But always remember only one expression, that Q value will be in terms of the daughter nucleus, I mean the nuclear mass of the parent particle minus nuclear mass of the daughter particles. So if you just remember that one, then we can just simply convert the nuclear mass into the atomic mass, or atomic mass into the nuclear mass to get the answer. Okay. So this is the question, and so if you have any doubt you can ask me, or otherwise we can go to the next question. Next question is very similar, so that's why maybe we can go for a little bit wrap up like thing for the first question, I mean from the previous question. Okay, so if there is no question, then I can go to the next question. Next question is this one, question number 6. I hope there is no question. Okay. So in the beta decay of radium, see here they have given that 88 and 89 number. So we will not bother about x and x plus 1 like thing. So in the beta decay of radium, 88 230 to 230 to AC 89 230, the maximum kinetic energy of the electrons emitted is found to be 317.529 keV. Just see the unit here. It is not in MeV, it is given in keV. So obviously we have to remember this one. I mean we have to be careful about the unit. Okay. If the atomic mass of radium 88 to 30 is this one, the atomic mass of AC is how much? So as right now we have just explained that for the beta minus case, the Q value in terms of atomic mass will be nothing but the atomic mass of radium minus atomic mass of AC. So we will just simply do that one, or otherwise if there is any doubt, or if you don't remember that what will be the value of Q in terms of beta minus or beta plus case, then just you need to remember the nuclear mass calculation, and then you just need to change the nuclear mass to the atomic mass to get the actual expression. Okay. So for this case, Ra AT equals to Ra nucleus plus 88 Me, because the Z is 88. AC atomic equals to AC nucleus plus 89 Me. Now Q value is Ra nucleus minus AC nucleus minus Me. So let's see that Ra atomic nucleus was how much? Atomic minus 88 Me, minus 88 Me minus AC atomic okay, minus 89 ME minus ME. So how much it will be? RA 80 minus AC 80, then C minus 88 ME plus 89 ME minus 1 ME. So that will be simply RA atomic minus AC atomic. So they are asking for the atomic mass of AC. So 7 now we will just do AC 80 is equals to Q value minus RA 80. So Q value is how much? Q value is 713. Okay, maybe I can write here. So AC 80 is equals to 713. Okay, 713.529 keV. That can be written as 0.713529 MeV. Okay, so that will be simply 230.037056 minus 0.71359 divided by 931.5. This whole U. Why I have done this one to keV to MeV? Because 1 U equals to 931.5 MeV. So it is given in MeV unit. And this is given in keV unit. So we have to convert that keV to MeV, and after that we will convert this MeV to U. That's why I have written here 0.713529 divided by 931.5. As a whole, it will be in U unit. And this should be subtracted from 230.037056. So let me calculate that one. 713.529 divided by 931.5. It should be, extra, I can write it here also. 230.037056 minus 0.000766. So 230.037056 minus answer. So it is 230.03629. 03629. Okay, so that means A. U. So is it understandable? Or if you have any question, you can ask me. So basically here what we are doing, we are just writing the Q value expression in terms of, at the very first in terms of nuclear mass, and after that in terms of atomic mass, and we have just converted the nuclear mass into atomic mass or atomic mass into nuclear mass to get the actual value whatever they are asking for. And also with that we have just changed the unit in terms of U, and like if wherever it is in the unit of MeV, then we have converted that one into U by dividing 931.5. And if it is in a keV unit, then first we just need to change that one in MeV unit, and after that we have converted that one in U unit by dividing that by to 931.5. Then we just knew the answer, whatever the options are given here, which one will be the correct. Okay, so maybe we can go to the next question. Okay, next question is, in the beta decay of Tc99 to Ru99, the maximum kinetic energy of the electrons emitted is found to be 4.89 MeV. If the atomic mass of Ru is this one, the atomic mass of this one is how much? That is very exactly similar whatever that the previous two questions were there, right? So for this case also, for this case at least I will not tell the exact, the full derivation. I will just write the expression. So it is again the atomic mass and the beta decay is there. So beta decay means obviously beta minus decay they are talking about. But for beta plus decay there will be a little bit different one. So for beta plus decay maybe there will be some question on that, or if it is not there then I will talk, if the time permits then I will talk in later also. Like what will be for the beta plus case in terms of atomic mass. But as it is given in beta minus decay only, then we can write it simply as right now we have seen that for this decay what is there, Tc going to Ru plus E minus, right? So the Tc atomic minus Ru atomic. So this is the case. Now Q is like 4.89, which is equals to Tc atomic. Tc atomic, okay, so Tc atomic they did not mention here, so Tc atomic I need to calculate. And Ru atomic they have mentioned 99.9987360 U. And this is in MeV, just remember these things because obviously it will not be correct otherwise. So Tc atomic will be 99.9987 how much? 4.89. 4.89 divided by 931.5. Okay. I already told you that why I have just divided that one by 931. So plus, let me calculate here, 4.39, no, 4.89 divided by 931.5. So it will be 0.005249 there are more decimal ones there. So plus 99.998736. So it will be like 100.0039856 U. So the atomic mass of Tc is, answer is 100 point, okay, 0039856 U. Okay, so this is the atomic mass for Tc-99. Maybe till question number 7 all the questions are explained and you understand that one very clearly. And after that we will go to the next question, question number 8. Okay, fine. So question number 8 is atomic masses of Rn and At are this. The Q factor of the beta plus decay. Okay, now there is a beta plus decay. Till now we were talking about beta minus decay, and for beta minus decay we concluded that in the terms of atomic mass, Q value will be the atomic mass of the daughter particle. Like for this case, let's say Rn minus atomic mass of At only. But for beta plus decay, that will be little bit different. So what will be for the case of beta plus process, that we will calculate right now. Okay. So maybe I am just writing here for in general case X, Z, A, Y plus beta plus means E plus. So if I write here in terms of Z and A value, that will be 1, 0. So if it is ZA, then obviously it should be A. Now what will be the value of here as a Z value of Y? It will be, can anyone tell? Z plus 1 or minus 1? Plus 1 or minus 1? Is it correct? Am I audible? correct? Z plus 1, or it should be Z minus 1, or it will be only Z. Which option should be there for Y? Can anyone unmute yourself and tell me? Anyone? Hello? Will it be Z plus 1?
It will be Z minus 1.
Z minus 1, correct, because this is 1. So obviously Z minus 1 plus 1, it will give us Z. So Z plus 1 will not be the correct one, Z will not be the correct one, that will be Z plus 1 simply, right? Okay, so now we got to know that for beta plus case, this is for beta plus case. So for beta plus case, x z a is going to y z minus 1 a plus e 1 0. Okay. Now coming to the Q value calculation. For Q value calculation, I told you that x nuclear mass minus y nuclear mass minus m of E. Now see, m of E means electron mass and positron mass are exactly same. So m of E can be written as electron mass as well as positron mass. So I have just written here as me. That's it. But in terms of atomic mass, what it will be? So x atomic, that will be x nucleus plus z into me, right? Because for x the z is the proton number. Now for y atomic will be y nucleus plus, what will be here? Z minus 1. Okay, Z minus 1 me. Okay, so Q value will be, so in terms of nuclear mass, what will be there? X of atomic minus Z into me, okay, minus y of atomic plus Z minus 1 into me minus me. So if I write this, x at minus y at, now see, minus z, okay, oh, that will be minus, sorry, that's why I told this is minus, because this one is there, so it will come here, so it will be minus, right? So minus z plus z minus 1. So if I just write here a little bit small one, minus z plus z minus 1. So how much it will be? Minus 1 only. So minus me minus me. This minus is also there. Let me write here me as up this one. So you can see here minus me from these two, and one minus me is coming out. So minus 2 me. Okay. So x at minus y at minus 2 me, that will be the Q value for beta plus decay. So I have written here also mass of Rn, that means atomic mass of Rn minus atomic mass of acetine minus 2 into me will give the Q value for this calculation. Mathematics. Is it fine? Because they are asking that what will be the Q value in terms of atomic mass of Rn, atomic mass of acetine, and we formulated that Rn atomic minus At atomic minus 2 into Me. So the answer will be 204.99172 minus 204.98607 minus. Now see Me. Me was how much? Me was 0.511 MeV. So it will be like 2 into 0.511 divided by 931.5. So whole will be in U. But they are asking in ABB unit. So okay, it's fine. Whatever it will get, that will be multiplied by 931.5. That's it. So let me calculate this one. 204.99172 minus 204.98607 minus 2 into 0.511 divided by 931.5. Okay, so this is 4.55 into 10 to the power minus 3 U. So if I convert it in MEV, so that should be multiplied by 931.5. It will be 4.240975 MeV. So the options are like 4.24. So that means this one will be the correct one, B. Okay. So we need to remember what will be the Q value in terms of atomic mass unit for beta plus and for beta minus. For beta minus process, it was in simply the difference between the two heavy parent mass as well as the daughter mass atomic mass. But for beta plus process, the expression will be the atomic mass of the parent nucleus, the atomic mass of the parent particle minus atomic mass of the daughter particle minus 2 into Me. Okay. So there is a difference between beta plus process expression and beta minus process expression. We need to remember that one in terms of atomic mass. But in terms of nuclear mass, it is exactly similar, that the nuclear mass of parent particles minus the nuclear mass of daughter particles will give the Q value. Okay. So I have written here the expression. Okay, fine. So now you can come to the next question. Again, it is simple. The atomic masses of Mg and Na are this one and this one respectively. The Q factor of the beta plus process is how much? So for beta plus process, as we already did right now, it will be like atomic mass of Mg minus atomic mass of sodium minus 2 into Me. We have to remember 2 into Me factor will come for beta plus process, 2 into Me factor will not come for the beta minus process. So for beta plus process, Q will be like Mg atomic minus Na atomic minus 2 into Me. So the value will be like 23.98504 minus 23.87304 minus 2 into 0.511 divided by 931.5. As a whole, it is in U. If you have any doubt, you can just ask me, so that I can also feel you understand a little bit. Okay. 1.097 into 10 to the power minus 3 U. All volume be in U. So 23.98504 minus 23.87304 minus 1.097 into 10 to the power minus 3. So this will be 0.110903 U into 931.5. So it will be nearly 103.306 MeV. So this is the case. Up to this, is there any question? Because we are right now in question number 9. So maybe there was 9 questions has already discussed. So do you have any doubt on that, or otherwise we will move to the next question?
No, ma'am, I understand.
Yeah, you understand. Very good. Okay, so maybe we can go to the 10th question. What is the Q value of beta plus T? Okay, exactly similar. so what we'll do? We'll just write the expression and after that we'll calculate, right? So the Q value will be IR of AT minus OS of AT minus 2 into ME. Just remember, I told you so many times, just remember that 2 ME factor. Okay, fine. So this is simply mathematics. 187, 955, 8382 minus 2 into 0.511 divided by 931.5. That will be whole in U, and then you will convert in MAP. So let's calculate that one quickly. 187.958853 minus 187.95588382. So this is 3.0148 into 10 to the power minus 3 minus 2 into 0.511 divided by 931.5. So it will be 1.097155 into 10 to the power minus 3. So 3.0148 into 10 to the power minus 3 minus answer. So it will be 1.917644 into 10 to the power minus 3 in U unit. So in MEP unit it will be multiplied by 931.3. So it will be some 1.78 MEP. Okay, fine. So this is the thing. So 1.78 MEP. So 1.78, okay, it was 1.7862. So 62 means obviously it will be 1.79 MEP. This is 1.79. Okay. Okay. So till now there was whatever the expressions was there. Based on these expressions, we just calculated different. With the different numerical values, we have just calculated some mathematics. That's it. Now maybe it will be little bit different coming here. Yes. Now here it will come as little bit different. So after question number 10, I hope everyone understand clearly all these things, and after that we will start the question number 11. Okay. So question number 11. Consider the beta decay. K46 IP equals to 2 minus goes to calcium 46 IP equals to 0 plus beta minus. Is this an allowed or forbidden big decay? Is it Fermi type or Gamoteller type? And there are 4 options: allowed Fermi, allowed Gamoteller, forbidden Fermi, forbidden Gamoteller. So I hope all of you has already attended the Professor Paulus Paulo's lectures, where he was discussing about what is Fermi type and what is Gamoteller type, what is the allowed decay and what is the first forbidden and second forbidden decay. So I have made a table. In that table you can understand all these 4 or 5 types of decays in one frame. Okay, and what will be the condition? Let's say what is the condition for allowed decay, what is the condition for forbidden decay, what is the condition for Fermi type decay, what is the condition for Gamoteller type decay. So I have a table where I have just mentioned all these things in a compact form. Okay, So just see the form, just see the table, and after that we can understand, we need to understand the question from the table. Okay. So this is the table I have made here. It's a very simple small table. Transition in the first column, allowed transition or first forbidden transition. Obviously there is second forbidden and higher order forbidden also present. There are different transition. I mean, if it is a allowed transition or first forbidden transition or second forbidden transition, it's already given in the different conditions. But till now in that table, I just mentioned the allowed transition and the first forbidden transition. Okay, fine. Now coming to Fermi rules. Fermi rules is what? I have written here delta I. This is delta AI. Okay, this is delta I. So delta I should be 0. If it is 0, then it will be allowed. As well as, okay, so these two should be satisfied simultaneously. That means in Fermi rule, if it is allowed, it should give these two conditions. One condition is delta I equals to 0 and parity should be no change. That means, let's say, just a minute. Okay, so Fermi rules is like that. These two should be simultaneously satisfied. For allowed transition, allowed Fermi transition means delta I should be 0 as well as parity should not be changed. I'm just explaining this table right now, and if there will be some problem on that, then on that basis I will explain the table again. Now coming to the Gamow-Taylor rule. For Gamow-Taylor rule, if it is a allowed case, allowed decay, then what will be the condition? The condition will be delta I should be 0 or plus minus 1, where 0 should be except 0 to 0. And Gamow-Taylor rules means parity should not be changed. Obviously it will you can't understand right now maybe what does this means, parity change and all these things. So maybe I can take an example, and after that it will be very much understandable to all of you. So let's take the example of this question, whatever it is given. So IP of K and IP of CA is given. So I am just writing here IP was 2 minus, IP is 0 plus right now. Okay. So IP, let's say this IP. So IP was 2, what was that? 2 minus and 0 plus. So 2 minus 0 plus, right? So IP for parent particle was 2 minus, IP for daughter particle is 0 plus B minus, electron is also there. But right now we will not talk about electron, because this is a free particle. We will talk about only the heavy massive particles, which is 2 minus and 0 plus spin parity. So if 2 minus and 0 plus is there, previously I was 2, right now I is 0. So what is the value of delta I? Delta I will be 0 minus 2, that means minus 2. Delta I is minus 2. Now see the table here. Delta I should be 0 for allowed in Fermi rule. So this case is not correct for allowed Fermi. Now coming to GT of allowed. Allowed transition in Gamow-Taylor rule is 0 plus minus 1. That is also not correct for delta I equals to minus 2. So this will also not be correct. Now coming to first forbidden. First forbidden with Fermi rule is 0 plus minus 1 should be delta I. But here delta I is minus 2, that means it will also not be correct. Coming to here, GT, Gamow-Taylor rule in first forbidden decay. 0 plus minus 1 plus minus 2. and here delta I can see as minus 2. So this can be the correct option. That first forbidden in GT rule, Gamow-Taylor rule. Okay? But again, I told you these two should be satisfied simultaneously. So if this column is satisfied, that means this one also be satisfied, also have to be satisfied. Now see it is satisfied or not. This is about the parity. So the parity, previously the parity was negative. Now the parity is positive. So that means parity change is yes. This is actually like parity change. So previously the parity was minus, now parity is plus. So parity has changed here. So this condition and this condition, these two simultaneously satisfied. That's why it is the first forbidden decay in the terms of Gamow-Taylor rule. So first forbidden and Gamow-Taylor. Do you have any doubt on that in that question or in that table? I will talk to later with the table also, but for this case, whatever the question was there, for this question the answer will be forbidden and Gamow-Taylor. Is it fine for all of you to understand with the help of this table? Yes? Can anyone confirm yes? I'm audible or not? Maybe. It's fine?
Yes, ma'am, you're audible.
Yeah, it's fine. Like Gamow-Taylor with the first forbidden. Or do you have any doubt on that? If you have any doubt, you can ask me. I can solve the problem, whatever you have doubt. Okay, maybe we will go in the next question also. That will also be the same type. So maybe it will be a more clear for the next question. Or this question is also fine. Just tell me the doubt. I hope there is no doubt, or is there any doubt you can tell me. See here basically what we are doing, IP was given, we are just calculating what will be the value of delta I. If delta is minus 2, we got that delta is minus 2. If it is minus 2, that means this is satisfied in this table. In this table means Gamow-Taylor rule with first forbidden decay, and as well as this also should be satisfied. So this is what? This is nothing but the parity change should be yes. So here previous parity was minus, daughter parity is plus. So yes, parity has changed. So that means this condition and this condition both are satisfied simultaneously. That's why we can tell that whatever the potassium 46 to calcium 46 plus beta minus decay is there, that is first forbidden with Gamow-Taylor rule. Okay? Okay, maybe we can go to the next question, then also you can understand clearly, more clearly. So, say this is also a case. Consider the beta decay. Sodium 26 3 plus going to Mg26 0 plus plus B minus and beta minus. Is this an allowed or forbidden decay? Is it Fermi type or Gamow-Taylor type? So first of all, we need to check that for Na and Mg. So what is IP? IP is 3 plus, it is 0 plus. Okay. So what will be delta I value? Delta I value is 0 minus 3. That means minus 3. And parity. Okay, first of all, if it is a plus, delta I equals to minus 3, that means we can go to that table. Yeah, in the table it's not mentioned here what will happen in the +3 case, but as I have written here this question, so it will come here, it will be like second forbidden. I did not write that one, so this is, it should not be done. Okay, fine. So for this, it will be, for this case, it will be for Gamow-Taylor type, delta I should be +-3 and their parity should be no change. What does this mean? This means that here you can see our sodium is going to magnesium and electron, and then we have seen that delta I equals to -3. So if delta I equals to -3, that means I told you that if delta I is +-3, that means it will be a like second forbidden with Gamow-Taylor type, and it should also be satisfied one thing, that parity should not be changed here. Parity no change. Now we will see that parity is changed or not. Here the parity was previously positive, in the daughter also it is positive, so that means parity is not changed here. So the second forbidden with Gamow-Taylor type, as it is written only the forbidden type, like it is not written that what first forbidden or second forbidden. So we will think that okay fine, forbidden means obviously it will be a forbidden one, first forbidden or second forbidden, whatever is there, that will be forbidden with Gamow-Taylor transition. Okay, so the table says that if allowed in Fermi rule, that means this one should be satisfied as well as this one should be satisfied. If first forbidden is there under Fermi rules, this one is should be satisfied, this one should be satisfied simultaneously. Here also, if this one is, if allowed in Gamow-Taylor rule, that means this whole should be satisfied simultaneously, this should be satisfied. For first forbidden in Gamow-Taylor rule, this should be satisfied simultaneously, this should be satisfied, like that. Okay. Okay, so in the next also maybe the same question. Okay, no, it is a different question. Up to this, if there is any doubt, you can ask me, or we can go to the next question, because this next question is a little bit different one from the other questions. So maybe we can think a little bit more on this question. But before that, if you have any doubt up to this question, you can ask me.
Ma'am, there is no doubt.
Okay, very good. So now maybe we can have this question. This question is question number 13. Now see the question. The atomic masses of xenon 54, 136, 0 plus. This whole notation, what does this means? Obviously till now you understand what does this means. This means this means Z will be 54, A will be 136, IP will be 0 plus. So this is the notation for xenon in this case. CS this one and beryllium this one. Are atomic masses are given here as this and this respectively. The values are given in the brackets. Oh, actually it will be IP values. The IP values are given in the brackets, as I already told you. Which of the following statements are correct? Okay, very good. So let me go one by one. The first option, the single beta decay of xenon is not energetically favored. The single beta decay of xenon is not energetically favored. They are demanding that one. Is it correct or not? We have to check. Energetically favored means any nuclear decay should be energetically favored when the mass of, let's say x is going to y plus z, not z actually, I can write it like w, because z is the atomic number, so maybe it will be a little bit confusing. So let's say x is decaying to y plus w. So energetically favored means m of x should be greater than m of y plus m of w. At least, I mean at rest, if it is at rest. Okay? So like that. Or it can be like total mass is like m of x should be greater than m of y plus m of w. Now see, xenon, they are asking the single beta decay of xenon. So if xenon is going to do the beta decay, xenon has 54. 54? Yes. So if it will conduct in beta minus decay means beta minus decay. If it will conduct in beta minus decay, so the Z value of this particle, it is xenon, so the Z value of this particle, whatever it will be, that should be 55, because my beta minus is nothing but minus 1, 0. So to conserve the Z value, whatever this particle will be, that should be 55 Z value. Okay? So now coming to the Z value 55. Which one is Z value 55? Z value 55 has CS. So if we will talk about single beta decay of xenon, that means beta minus decay of xenon, then it should go, xenon should go to cesium. Xenon should not go to barium, because barium has 56 Z value. So xenon should go to cesium. Okay. Now the energetically favored or not, that we have to check. So energetically favored means, I told you that mass of the xenon should be greater than mass of cesium at least. So now check mass of xenon. Mass of xenon is this much, 135.90722. Mass of cesium, 135.90731 U. So now see, 90722, 90731. So this one is more than this one. So xenon cannot go to cesium by beta minus decay. It will not be possible energetically. So it is not energetically favored. Is it understandable? Energetically favored means the mass of the parent particle should be at least greater than the mass of the daughter particle. Here the mass of the xenon is not greater than mass of cesium. So xenon cannot be decay as cesium through beta minus decay, single decay. Is it fine? The first option, yes? Please tell yes or whatever. The first option is understandable. Okay, it is not energetically favored means it's correct. Sorry. There is no not, it is right now. So the statement is correct. It is exactly not energetically favored. That I was trying to tell you. So single beta decay of xenon is not energetically favored. Okay. Now coming to the second option. The single beta decay of xenon is energetically favored but is highly forbidden, involving large orbital angular momentum of the electron neutrino system. So first of all, you understand that it is not energetically favored, as we already discussed. So there is no option B as a correct one, because it is saying that the xenon is energetically favored with a single beta decay. So it's not correct. We will not think about the other part also, because the first part is already wrong. Okay. Now double beta decay of xenon is an allowed reaction which is energetically favored. They are asking that one. Double beta decay of xenon. Now coming to double beta decay. Double beta decay of xenon means double beta decay. So what does this mean? This means that whatever this will be there with double beta decay, that means 2 beta will be there. So 2 beta means what? It is nothing but E minus 1 0 into 2. So what does this means? E minus 2 0. Actually it should not be E minus 2, like it should be like some, 2 into E minus 1 0. Okay. So whatever this will be there, that will be 54 plus 2, which is 56. Otherwise z value will not be conserved here. It is minus 2 right now. So 56 should be there. So what is 56 in this question? 56 is barium. So the double beta decay of xenon means xenon is going to barium plus 2 beta. So now double beta decay of xenon is an allowed reaction. They are asking that it is allowed reaction or not. So to know the allowed reaction or not, we have to check the IP calculation. So IP is 0 plus, IP is 0 plus. So 0 plus 0 plus, that means for this case delta I is equals to 0 and parity no change. Now come to the table again. Delta equals to 0, delta equals to 0 and parity no change. Delta is 0, parity no change. So that means it is an allowed one. You can see that this is an allowed one through Fermi rule. So whatever they are telling, double beta decay of xenon is an allowed reaction. Up to this sentence, this phrase, this statement is correct, which is energetically favored. Now we have to check that it is energetically favored or not. Xenon mass is 135.90722. Barium mass is 135.90458. So 722,458. So this is greater than this one. So maybe it will be a energetically favored reaction. So that means whatever the statement is there, it is correct. Double beta decay of xenon is energetically favored but is forbidden considering orbital angular momentum. That is not correct. If C is correct, then obviously it will not be the correct one because these two are contradictory to each other. So the correct option is A and C. Is there any doubt on that? I have explained each and every option elaborately so that we can have the knowledge which of the following statements are correct. Okay. Do you have any question? Yeah, I have written here the answer also, A and C. If you don't have any question, you can go to the next question probably, or otherwise if you have any doubt, just tell me. I told you so many times. Okay. Okay, so this is the question number 14. Which of the following statements are correct? In beta minus decay, an antineutrino is emitted along with the electron. Okay, let me go one by one. In beta minus decay, an antineutrino is emitted along with the electron. Very good. So X, Y, beta minus, that means electron will be there. Now there is one neutrino or antineutrino, they are asking for that. So in terms of lepton number conservation, whatever the lepton number is there, let's say this is 0, this is 0, this is 1 because electron-lepton number is 1. So that should be minus 1 to conserve the lepton number. So whenever an electron will come, with that an antineutrino should come. Because this is a minus 1, right? So neutrino has a lepton number plus 1, but antineutrino has lepton number minus 1. So whenever the electron will come out, one antineutrino should be come out with that to conserve lepton number. So this statement is exactly correct. In beta plus decay, the emitted positron has fixed kinetic energy. It's not correct. Why? Because for positron, that beta plus decay, for positron case, E plus will come out. With that, one neutrino will come out. And this neutrino and E plus will share the energy what is left. What is the difference between X energy and Y energy? So there will be a spectrum like thing. It will not be, the energy of the E plus will be a spectrum like thing. So it will not be a fixed kinetic energy. Okay, because the neutrino is also there and it will also take some energy which will depend on the value of, on the energy of X, Y and E and mass energy like that. So in the beta plus decay, the emitted positron has fixed kinetic energy. That is not correct. Kinetic energy of the electron emitted in beta minus decay is independent of the mass of the daughter nucleus. Kinetic energy of the electron. Okay. So beta minus decay is this one. So kinetic energy of the electron, this kinetic energy of this particle is independent of the mass of the daughter nucleus. No, it is not correct, because the kinetic energy is nothing but, see, the total energy should be conserved. Total energy of X should be conserved. That means total energy of X should be equal to total energy of these particles. So total energy means what? Kinetic energy of X plus rest mass of X should be equal to kinetic energy of Y plus rest mass of Y plus kinetic energy of E minus plus rest mass of E minus plus kinetic energy of nu E bar plus mass of nu E bar. This is the thing. So what will be the kinetic energy of electron? That is a function of kinetic energy of, the mass of the daughter particle, the daughter nucleus. So this depends on this one, this depends on this one, this depends on this one as well. So electron kinetic energy is not independent of the mass of the daughter nucleus. This is also not correct. If it is energetically possible for an atom to undergo beta minus decay, it will never be energetically possible for it to undergo beta plus decay. This is the fourth expression, statement. So the fourth statement is, if one particle undergo beta minus decay, it will not be possible to undergo beta plus decay. Is it correct or not? Let me see. Let's say X particle undergoes beta minus. So if it is beta minus, that means X is going to Y plus electron. Okay, plus nu E bar. So that means what? Mx should be greater than My. Now for beta plus, X, okay, this is Z plus 1. X is going to, let's say, W, another particle, okay. This is Z minus 1 plus E plus nu E. So beta minus for this, Mx should be greater than M omega to happen this one. So that means if X is decaying through beta minus as well as beta plus, that means what? That means M of X should be greater than M of Y as well as M of omega. Otherwise it will not be possible. Right? Now see the Z values here. And A. A is there, A is there, A is there. So if X is greater than My, then obviously X will go to Y. But it is not simultaneously possible that X will go to omega, because if mx is greater than my, then obviously it will go to y only. It will not come here. These two simultaneously cannot be possible. So if one particle is giving as beta minus, and this same particle cannot give as a beta plus as a stable one. It will not be possible energetically, but it will be possible from the concept of Fermi type and Gamow-Taylor type. That can be possible, but in terms of energetically calculation, it will not be possible. So whatever the fourth one is there, if it is energetically possible, it will never be decay. Okay, it will never be decay. That means this statement is correct. Beta minus, beta plus, energetically, simultaneously, it will not do simultaneously. Energetically, if I talk. So, whatever the option 4 is there, that is correct. So, option 1 and option 4 is correct. Option 2 and option 3 are not correct. Okay. So, should I go to the next question? This is also a similar question like with the table. So maybe IP was 0 minus, IP was 0 minus. So delta I is 0. Parity, it is negative. So parity is no change. Now see the table again, delta is 0 and parity no change. What does this means? Parity is 0, delta is 0, parity is no change, which is means by allowed region in Fermi type rules. So this is allowed and Fermi. This is a correct option. Maybe this is the last question. This is the last question. This one is very similar to whatever it was there previously. Consider the 4 isotopes. Am I audible? I think I am audible. Yes. Consider the 4 isotopes: boron, carbon, nitrogen, oxygen, with masses this and this respectively. Their nucleus spins and parities are 3 by 2 minus, half minus, 3 by 2 minus respectively. Which of the following sentences are correct? Carbon 13 is stable against both beta plus and beta minus decays. Okay, see this question. It is stable against beta plus and beta minus. I told you that energetically it is not possible. Even also you can see here also that it is not energetically possible to have beta plus as well as beta minus simultaneously for carbon 13. Why? Because beta plus means carbon will go to boron. Beta minus means carbon will go to nitrogen. Now see energetically, carbon has the mass this one. This one is carbon mass. This is boron mass. This is nitrogen mass. So this 0.0033, 0.01, 0.005. Obviously for this case, beta plus as well as beta minus, nothing is possible energetically for carbon. But let's see it is stable or not. Stable means IP. We have to check IP. So IP is half minus. Here IP is 1/2 minus. Here 3 by 2 minus. So half minus can go to half minus. That is fine because just right now we saw delta I is 0 for that case. Half minus to half minus. That means IP delta I will be 0. And parity will be no change, right? So that means it is allowed under Fermi rule. Okay, so beta not energetically but stable or not, that I can tell from IP consideration, and it is stable that carbon and nitrogen beta minus case. Now coming to beta plus case. So beta plus case, I half minus 3 by 2 minus. So half minus 3 by 2 minus. So delta I is 1 and parity no change. So delta I is minus and delta I is 1 and parity no change. Let me see the table. Delta I is 1, parity no change. Is it allowed or not? Okay. See, delta I is plus minus 1, parity no change. It is allowed under GT rule. So whatever the rule is there, Fermi rule or GT rule, irrespective of these rules, it is a allowed transition. Okay. So this beta plus is allowed by IP consideration. So now maybe I am going again to that question. Yes. So carbon 13 is stable against beta plus and beta minus decay. That is correct. But stable means in which sense it is not energetically favored, but in terms of IP calculation it is favored. So that's what I am telling, it is against stable. Beta minus of nitrogen 13 is not favored energetically. However, its beta plus decay is sorry, because I was disconnected maybe for a while. So okay. Yeah, what I told, carbon 13 is stable against beta plus as well as beta minus decay. Now coming to the second option, beta minus decay of nitrogen 13 is not favored energetically. However, its beta plus decay is energetically allowed. Is it correct or not? Beta minus of nitrogen 13. Nitrogen 13 beta minus decay means nitrogen will go to oxygen. Yes? So beta minus is this one. Now see the energetically favored or not. Nitrogen has mass 13.00574. Oxygen has mass 13.02482. So nitrogen will not go beta minus with oxygen because it is not energetically favored. Mass of nitrogen is less than mass of oxygen. So whatever it is saying, it is not energetically favored. However, its beta plus decay is energetically allowed. Let's say beta plus. Beta plus means nitrogen can go to carbon. That is beta plus. Let me write here like that. Yes. Nitrogen can go to carbon. Now see the energy. Nitrogen has mass 13.00574. Carbon has 13.00335. So this one is greater than this one. So that means nitrogen can go through beta plus decay with carbon. So that is correct. Whatever it is saying, beta minus is not of nitrogen 13 is not favored energetically. However, its beta plus decay is energetically allowed. Okay. So this is correct. Now beta minus of boron 13 is most probably a gamotelar type decay. Beta minus of boron 13. Boron 13 beta minus. So boron 13 beta minus is this one. Boron will go to carbon. So boron carbon 3 by 2 minus half minus. So delta I is minus 1, parity no change because minus minus. So now you can see beta minus is most probably gamotelar type decay. Obviously it is a gamotelar type decay because in the gamotelar type table you can see It will, for gamoteller type, if it will be allowed when delta I will be plus minus 1 and 0 and parity will be no. So this is correct. Now beta plus decay of oxygen 13. Oxygen 13 beta plus, that means it will come to nitrogen. Oxygen beta plus decay of oxygen 13 is energetically allowed. Energetically allowed it is or not. 13.02482 was the oxygen mass. Now nitrogen mass is 13.00574. Mass of oxygen is greater than mass of nitrogen, so that means it is energetically allowed, but it is a forbidden decay considering the angular momentum conservation. Now see the angular momentum conservation. 3 by 2 minus half minus. So oxygen, nitrogen, 3 by 2 minus half minus. So delta I is minus 1, parity no change. So it is allowed because it is allowed by gamoteller type, as we already seen. So whatever the statement is there, beta plus decay of oxygen 13 is energetically allowed, up to that it is correct. But it is a forbidden decay considering the angular momentum conservation, that is not correct. So this statement is also not correct. So the correct statements will be 1 and 2. No. 1, 2 and 3. Okay. So 1, 2, 3 will be the correct options. 1, 2, 3. So then I think this, okay, up to this it is there. So do you understand this question? I hope yes or no. Whatever the answer of yours, you can tell me. So these are the total 16 questions I had for today's session. Maybe I am going little bit in the backward side. If you have any doubt on these questions, just ask me. This is the 16th question. This is the 15th one. This is 14th. This is 13. This is 12. This is 11. This is 10. Yes, I am still there. So okay, this is question number 9. This is 8. This is 7. This is 6. This is 5. This is 4. Oh, sorry, I was again disconnected. So I'm unable to share the screen till now, but yeah, it's fine or not. Like I have already finished the 16 questions today's sessions. So if you have any doubt, you can ask me on these 16 questions, or maybe we can stop today's class and after that we will meet in the next class. Actually, I could not share the screen right now because if it will be shared, then again it will gone. So. Is it fine, or do you have any doubt on these 16 questions, or otherwise it's fine? I'm audible, right?
Ma'am, I have no doubt.
Yeah, you don't have any doubt. Okay, fine. Okay, so maybe we can have the next class on when? Next class on 23. So till now, bye bye. Good night.
Thank you so
Thank you,
much,
ma'am.
ma'am.
Good night.
Good night.